Hi, hello. Welcome to this new webinar about CivilFEM 2017, this new version of CivilFEM powered by Mark. Thank you all for attending this webinar. This webinar will present an advanced thermal structural coupled analysis using this software. Roman Martin and Ronald Siat will be the presenters. We hope you will enjoy and you can use these features for your civil engineering analysis and other type of mechanical analysis.
Well, the target of this webinar is to have an overview of the advanced nonlinear capacities of CivilFEM in thermal structural coupled analysis. Well, the thermal structural coupled analysis involves calculating the temperature distribution within a structure, steady state or transient, due to thermal boundary conditions. These boundary conditions could be conduction, convection, or radiation, and to determine the thermal effects on the structure, such as permanent and induced thermal stresses, and the combination with the structural stresses due to other structural loads, gravity loads, and the effects of these thermal effects on the behavior of the structure, the combination of both. And well, as I said, the aim of this webinar is to present the advanced capabilities of this thermal structural coupled analysis with some examples such as early age thermal cracking in concrete due to heat of filtration at early age, also effects of ambient temperature and solar radiation, and we will see other examples of fire protection. We will have an overview of some examples. We don't have much time to see in detail, but if you are interested in any of these examples, you can ask us for more information or for some demos. Well, the CivilFEM thermal structural features that we have is first about materials. We have thermal orthotropic material properties, that is thermal conductivity and specific heat that are orthotropic. Also material nonlinear behavior, that is temperature-dependent properties, elasticity modulus, yielding stresses, and some other data are temperature-dependent. So we can perform a completely nonlinear analysis. The type of thermal boundary conditions are convective, conductive, and radiation, and they can be applied on any type of elements, cells, solids, and beams and links. And this analysis can be steady state and transient thermal structural coupled analysis. Of course, you can solve only thermal analysis if you are interested only in the thermal results. And of course, we have post-processing graphic interface, and that we can plot all these results: temperature, thermal flux, with vector plots, and well, all the typical data. The examples we are going to see is first an example about the mass concrete block placement, where we analyze a transient thermal structural analysis and the effect of heat hydration. And we will calculate the thickness of the new block, just the maximum thickness that we can have, considering temperature and stresses inside the model. Next example will be arc dam and the effect of seasonal temperatures on the dam. During 2 years, the effects of cold and warm and heat on the dam due to seasonal temperatures, and the crack developments on the dam and movements. The next example, we will see fire protection analysis in concrete and steel structures. We will see different possibilities of protection and time that is needed for the building to collapse due to fire in different compartments. And the last example will be a natural liquid gas tank, that is a post-tension concrete tank, and the effects of temperatures, the gradient inside minus 170, outside ambient temperature, and the steady state thermal analysis to calculate the gradient inside and combining the thermal stresses plus structural stresses, and after that performing a code checking. Well, let's start with the first example. This will be a transient thermal analysis, thermal structural analysis, where we apply self-weight only, and also the effect of heat generation from cement hydration. The aim of this example is calculate the thickness of the layers. We are going to solve just, this is the example, and we are going to solve just 1/4 of the model. So here in this phase we have symmetry, and in this other, this is a plane of symmetry. So we are solving only 1/4. We will have on top ambient temperature. So we have here some boundary conditions of the ambient temperature on both sides. On lateral sides, we have other thermal conditions, because we have here the caching, and symmetry conditions in these other sides. So if we if we open the software, CivilFEM 2017, and we are going to open the first model, which is a block of 1.5 meters thickness. Well, here first, as we are solving a structural thermal analysis, here in loads we can apply thermal boundary conditions and also structural boundary conditions. This is a nonlinear transient analysis, so we also apply initial conditions. In this model, the initial condition is initial temperature in all the model that is 16.5 degrees in all the model. Well, this is in other units, and that is all. As I said, we have symmetry boundary conditions in these sides, and the other boundary conditions on the model. Well, first, flux. This table is the concrete thermal flux that follows these tables, and this is in hours. So this is the temperature, and this is the thermal flux, and this is the hours, and this is the effect of cement hydration. And this is the air. If we see the boundary conditions of the air, the ambient air, and we plot. This is the ambient temperature that we can see there's a variation between about 22 degrees during the day and about 6 during the night. This is in hours. We can plot this graph in days, so we can see we are solving for 5 days, and we have the day and night variation. So we are solving that boundary condition on top, and then convection in the both sizes. So these are also here you can see that the coefficients of the different properties are variable, and we can set them with a table. If they are constant, the table they will be a straight line. So after solving, here we have 3 options. The analysis class can be thermal structural, so we are solving both. The software is considering structural loads and also the thermal effect. And also we could solve only thermal, or both, or only structural. We are solving in this case both. We have here all the properties, the converging properties for the thermal analysis and also the structural analysis, tolerances, and check. Well, I'm going to load the first Excel file. This has been solved with different load steps. I'm going to see first the temperature. So as you can see, the results are created structural and thermal results. If we plot temperature in degrees, example, first day, this is the temperature we're having, and at the end of the 5 days, this is the last temperature, between 27 and 14. Well, let's analyze just during the 5 days the temperature on top, middle and bottom of the new block. So with the history plot, we load thermal results. Okay, here we have, and I'm going to plot node results that are temperatures. Let's see in which nodes I'm going to plot. These are in node 7664. This is the next one, 7359, and the next one in bottom, which is this other. So if we select them in the history plot, in degrees, centigrades, and minutes.
This history of results utility helps a lot when we have transient analysis and nonlinear analysis, so we can post-process using many variables. Can be time or can be some results versus another. And can be any result that is available in CivilFEM, it can be plotted.
Yes, here by default we are plotting results versus time, but we could select for x-axis any other result and plot any result versus another one. Well, if we plot temperatures in middle, top, middle and bottom, these are the temperatures we are having during these 5 days. We can see the first value, blue one, is on top. That's the ambient temperature affect the concrete temperature. The next one, which is the red, is in the middle, which is the highest temperature, and the green one is in the bottom. So we are reaching about 30 degrees centigrade. Okay, so we don't know if this temperature will generate cracking or any wrong effect on the concrete mass. So what we are going to do is just plot structural results, in example, stresses on the model. So if we go to the structural results, here we have, I'm going to plot now results in the elements. So all the results we are going to plot are in elements in top, middle and bottom elements. So it's this one, and the bottom one. So if we add the results, the history plot results, here we add. These are now end result. The value we are plotting is a maximum principal stress in megapascals, and the element, the 3 elements that we said we are going to plot the results, top, middle and bottom. Okay. So if we plot those results, here is the progress line. Well, we have many results and sometimes takes a few seconds.
Depending on the number of results on your machine, or you will always take more or less time in plotting results and generating videos.
So well, here we have the results and we can see the values on top. Well, we are applying also self-weight, so in top there is no stress due to the gravity loads. So it's only due to the temperatures, and we can see the day and night variations, and we can see the maximum stress is about 0.3 megapascals. In the others are under compression, so there is no problem. Well, for this earthly age concrete, well, the cracking stress is about 0.4 megapascals, so there's no problem in this model. The next model we have solved is, well, this is the thickness of this is just 1.5 meters. Here you can see this one. Save here. We have solved for 1.5, 2, 2.5, and 3. So if we go to the last, all models are the same. So we are going to plot the last one. Here we can see here in this last model, this is biggest, highest thickness. And well, if now we plot stresses on the model in the same way we did in the previous one, now the number of elements doesn't correspond, so don't correspond. So I have to generate just to select new element name numbers. So now if we check the element numbers we have for this situation, this is one of them. This in the middle, about the middle.
As CivilFEM can use parameters and can be combined using scripts, it's very easy to optimize this thickness, which is at the end the result that we want to obtain, which will be the optimum thickness and with the temperature variation.
Yes, this can be hydration. As Ronald said, this can be launched with a macro where the thickness is modified, it is solved different times, results are extracted. So this could be optimized with a macro and just you don't have to work so much, just a macro, solve it during the night and have the results.
Yes, you can have as many results of thicknesses that you need. Because this time it's only the thickness, but of course you can use another parameters.
Well, here we have the result, and we can see here that now stresses in the other model, the first with the thickness, the temperature were below 0.3, and this is over 0.4, which is the cracking stress. So we can see at 1 day, more or less, well, this is plot now in minutes, I can plot in days, which is easier to determine which is the, just to analyze which is the cracking stress. For day 1, the cracking stress is about 0.4 in this model. So we can see that for day 1, that is here, 0.4, it's about this cracking, so this could be over the limit. So for this thickness is too much and cracking will happen. If we go to the slides, we can see the comparison of these values between the different thickness. We have solved 1.5 meters, 2, 2.5, and 3 meters. So we can see here that in the first result, temperatures are reaching about 30 degrees. The second one, it's over 30, about 31, 32. The third one is about 33, and the fourth one is almost 35. So temperatures are a little bit higher, but let's see stresses. In stresses, the first one we can see it's about 0.3 megapascals, the maximum value for day 3. In the next one, this value just is increased from 0.3 to 0.38. So it is increased, but still below the limit. The fourth model is reaching 0.4, so that is more or less in the limit. And the last one here, you can see we have plotted with the tensile stress, the cracking stress for the different days, and you can see that these values goes over the limit. These values goes over the limit, so we will have cracking on the surface of these blocks, so the thickness is too high. So, well, we could just keep 2.5 meters, or if we need 3 meters, we need a cooling pipe just to put temperatures below this value. So that is the next step we have done, just defining some water pipe network inside this type of piping network inside concrete. This is the base, this is the new block, and this is the geometry, the way we have done it. As we are having two symmetry planes here, just these pipes will be just a part of these two lines, two levels of pipes. And solving, we're having this type of results. If we go to the model and open it, here we can see, if we hide this part, here we have the piping inside it. And well, we plot it again. Well, we plot it again. We have applied in these pipes water for the boundary conditions in top and bottom, and the temperature for the water inside these pipes are 10 degrees. But they are start being empty, and just water start moving just after a few minutes after placing concrete. So first we have the ambient temperature, and then when water starts moving inside, we have 10 degrees due to the water inside this piping. So if we plot results, I'm going to open an example, the last temperature result in degrees centigrade. And we can see here, well, the effect of these pipes. Well, the values are between 10 degrees and 25 degrees. 10 degrees, of course, around this piping, and here, well, the other values. So, well, now if we plot stresses in this model, now we are going to take the new values, structural stresses on the model. In this case, it is the same values, because we are having the same model where we have added the piping, but the elements and everything correspond to the same. And here we can see that in this case, well, we have these stresses below due to the compression that are below to limit, and in top we have this variation that are under 0.4 megapascals. So we can ensure with this piping that the temperature will be below the limit. So also we could stresses will be below the limit, and also we could plot temperatures. But we can go to the Excel file, to the PPT file. Let's see the comparison. This is without water pipe, and we can see temperatures are reaching about 35 degrees, and this is with water pipe. We can see that in the middle, it was the highest temperature in the previous model, and now the temperature is under the bottom temperature go below, and these are the temperature, and these are the stresses that, of course, are under the stress limit. So with this model, we can analyze with these capabilities any type of stresses due to concrete hydration, and residual stresses in the model, and also we could use these stresses combining with structural stresses to design a model, to take an example a slab with a high thickness, and to check and design by code, considering residual thermal stresses and also structural stresses. So this is one example. The next example is the analysis of thermal cracking development due to ambient temperature in a concrete arc dam.
Yes, we'll open the file first, so we can have first okay. So this is an arc dam, and it will have different loading of course, always the gravity and the hydrostatic pressures, but the most interesting loading is the variation, the seasonal temperature variation. What we have done is apply surface temperature tables during time, a transient thermal analysis, and we applied a two-year temperature table. We started with a warm year and later a cold year, and we applied it downstream and upstream. In one upstream will be the water temperature, which is the table here below, and we applied in days. So you can see here, well, almost first year to 360 days from starting from month of April. And in the what we call air temperature, that we'll show you later in the model, we apply another variation. So we will have two different temperature variation and during time in different places of the dam.
You can see that during the summer we have in water temperature we have about 12 degrees and the air 20 degrees. So well, it will have a gradient with higher temperature outside. And during the winter, the cold days that we reach minus 20 degrees, 25 degrees, the gradient is inverse in the other position. So this will generate the dam displacements on top and also the development of crack patterns on the dam, and that it could be a problem for the dam safety. So this model will be used for the dam safety investigation.
Yes, you can see that, as Roman said, that the water temperature will never below zero, and there will be the highest peak during winter time, which is minus 26. Okay, I'll open if we have here the model. We can see the soil and the part of the arc dam, and as I told you, with the different load groups will be the hydrostatic, which is just the pressure of the water. With the height of this dam is 95 meters. But the interesting loading is the what we told you about the temperature variation. Here you can see the different days, and we can see here, this is the as we explained before, how we set the different, we can use a table of course, a spreadsheet, the Excel spreadsheet, to show to insert all these points. Okay, we can solve always an transient analysis using this calculation time of 2 years.
Okay, well, now we can see the results. We are going to plot displacements. In example, if we load the large results, we have solved only structural results, also thermal analysis results, and combining both. So we are going to plot combining results, and here in example we are going to plot displacement in X direction due to the both thermal and hydrostatic pressure. If we just hide this part for not considering the soil, we can see that we have maximum displacements of about 13 centimeters in these sizes. Okay, we can also plot displacements in the model due to the ambient temperature during 1 year. So here in one of these nodes, example this one, and we are going to load the results. in this node, which is
1000.
okay, and we can also select other node, in example, in this side. Well, these are the displacements during the displacement that they are in for the different days, and in meters we can plot them in centimeters, in example, if that is easier for us to analyze, or in inch, in example, for just checking other units. We can plot in any units. Results also, the input could be in any unit type, and here we can see the displacement goes between -3 inches, variations till -1, and this is the displacements of the model. Okay, so we also can see that if the displacement that are generated due to these thermal variations in the model, and also we can see if there are cracking development on the model. So the results, if we load the first result, just an example, day 1, we can see, we are going to check instead of plotting the node style, we can plot for this day the cracking strains in the model, and we can see that for this day we have almost no cracking in these zones, just on both sides here due to stress peaks, but the beginning due to self-weight and hydrostatic pressure we have no cracking, but if we go to one of the last results, in example, this one, 46, we can see that there are some crack development patterns in the model. Here we can see that we have some cracks here on the dam due to this thermal variation. We can just modify a little bit the scale just to see these cracks, but well, we have these cracks development here in the center, and also here in these sizes of the inner part of the dam. So well, we could analyze the cracking sizes, the displacements of the dam, and to analyze the safety of this dam due to the ambient thermal variation. Also, we could include here a sun radiation in this surface, and just check the effect of that. So I'll check in the slides. Here we can see these crack patterns. This is the maximum crack width during this thermal variation, the ambient variation, which this is the value of these crack strains here, and that's the displacement on top of the dam.
Yes, okay. You can see that the maximum crack development are matches the maximum difference of temperature between the upstream and downstream due to the peaks of the temperature table that we have set. The peak in summertime and the peak in winter time.
Well, okay, the next example is about fire protection. We will analyze different options for fire protection. We have also many small examples where we can see. We will seek temperature-dependent material properties in this model, and we will analyze also the stability of structures in fire. We have a concrete beam model, a steel column model with a protection around, and after that we will see the building fire collapse, the stability of a building, applying this fire on different compartments. Here first in this zone, we applied the fire effect, and in this other zone. And we will see the stability of this building due to those fires. First we are going to open the concrete beam example. Here fire protection, concrete beam, and here if we open it, we can see the results. Here is a concrete beam. We have here the reinforcement and the concrete, and what we apply the boundary conditions here. We plotted the thermal boundary conditions are a fire, is a fire around it. Not on top, because this is holding a slab, and we suppose there's not thermal heating, but around it. And well, just we have solved, in this case, the transient thermal analysis, and we can see the results here. Now, plotted. And here we can plot the temperature, starting like this, the first minute 100 outside, and ambient temperature 20. So if we are in the time is in just here we can see as temperature is reaching inside during the time. So with this analysis we can deduce the time, the minutes we need to reach certain temperature in some points of the structure. In example, if we just plot temperature versus time, here, well, I'm going to load first the values. This has been solved in 15 of the steps, which is not much. And well, here node results, and well, we are going to plot the values in this node, in example, which is node for instead of days, minutes, and we can see, well, this is the temperature that we are reaching. In example, we are reaching 800 degrees centigrade after about 350 minutes. Okay, well, we can plot that also in hours, and let's see that, well, we reached that temperature in about 6 hours. Well, this model has not temperature isolation, so well, the temperature is reaching the reinforcement is reaching a high temperature very fast. So we could analyze other model with fire protection. If we open model, steel column, and thermal analysis for this steel column, we can see here. Well, here we have a video with the thermal variation inside the concrete, and well, now the model we are going to see is a column with also 100 degrees applied outside with a fire protection material, and we are going to analyze also the temperature that we need for reaching certain values inside the model. Here you can see we have now this model with this material, which is the isolation, and the heat properties, the heat transfer properties are these ones. We have orthotropic values that can be in X, Y, and Z, or constant values. And we have a specific heat definition, and also here the thermal conductivity definition for this material, and also the steel inside. So what we can do is we can repeat the same steps inside, the same steps in the other model, and just analyze thermal values inside the model. Just we are going to see this node in example. Well, we can see that due to this thermal protection, this curve is different than in the concrete. Just we need more hours, more time to reach those high temperatures. So well, the next step is solving. This is only a thermal analysis. The next step should be solving just instead of thermal structural analysis. And well, here for the steel, we could solve analysis with time-dependent temperatures, and these time-dependent temperatures are this one. For different temperatures, we can visualize in degrees centigrade. We have for 100 degrees, 200, 300, 400, different values. We have different stress-strain diagrams. We can plot them, and you can see the elastic limit, the yielding stress, is reduced due to temperatures. So we could apply to this model of a transit analysis and apply here on top to this model the axial force, bending moments due to my building, and here perform a nonlinear analysis and analyze the time we need for the backlink analysis. Instead of doing that with a simple example, we could apply it to the whole model. So here we have obtained this curve of temperature due to this protection. So what we can do is apply this curve, this temperature variation on the steel beam. We could apply as initial conditions to different parts of the model. So if we apply this curve, we don't need to model the fire protection material because we are considering applying these curves. And we apply to different parts of the model. We applied it and solve it. So we can see if we load those examples. Next example here, this one, the first one. We can see here we have applied those boundary conditions to these red beams and columns. So temperature is increased, and of course the material properties are, the stiffness is reduced until the collapse happens. So we plot all the structural elements. We open the first structural value, and we can apply it here in example equivalent plastic strain on the model. We can see here that for the first step there is no plastic strain in the model. Fire is starting, so temperatures are very low. But if we go to the last load step, we can see that due to this heat, here buckling is happening in these columns, and those columns are completely yielded and with buckling effects on all that part. But we can see the building is still has still some stability. It didn't collapse in this zone that it happened. Just this floor there are some damage in this floor, but not the completely collapse. And just checking the slides here, we can see results in both. The first applying only in this zone. Here we can see the video during the time that yielding starts here and buckling is happening in those zones due to fire. But there is stability in the building after the fire, after the time the fire has lasted. And in the last model, here we can see that fire is happening here on bottom, but instability of the whole building is happening, and the model stop converging here because the building completely collapsed. So with this CivilFEM, we can analyze also the instability in a whole building just when fire is happening in just different compartments of the model, and just to design the model for fire to prevent collapse during a minimum time. So this is other application of CivilFEM coupled thermal structural analysis. And the last example we are going to see is natural liquid gas tank. Well, this natural liquid gas is a post-tension concrete tank. This concrete post-tension tank has these tendons, vertical and circular tendons. The density of tendons is higher here in down and is going up. And this is the thermal insulation here inside. The yellow part is the material to avoid just high thermal effect on the concrete part. And in this model we are solving steady state thermal analysis plus structural analysis. Just steady state, we would like to just check the thermal gradient in the concrete and check and design by code. So we don't have much time to see this model. We can see in detail in future webinars, but after solving, as we have seen in previous models, we solve the thermal part, the structural part, the combining effects, and the stresses and forces and moments on the shell elements of the concrete tank. And after that, we can perform code checking, bending plus axial or shear reinforced amount calculation. Here are some results: reinforcement amount in X top duration in square centimeters per meter. Here we need higher amount, and also we can perform cracking checking. So, well, just as a summary, we can see that with CivilFEM 2017, we can perform nonlinear transient or steady state thermal structural analysis, and the future we have is thermal orthotropic material properties, that is thermal conductivity and specific heat. Also, these material properties can be nonlinear, that is temperature dependent properties. So we can perform a completely nonlinear analysis. Not only thermal conductivity and specific heat are temperature dependent, also other values as elasticity modulus, yielding limits, any other. The thermal boundary conditions we can apply are convective, conductive, and radiation boundary conditions on any type of the elements. And as I said, nonlinear steady state or transient. Thermal structural analysis coupled, or thermal or just structural, we can solve any, and just plot the results, plotting, listing, any type of, with vectors, any type of value. And well, we have seen, we have the main applications is any model that could have concrete, and we need to analyze the heat of iteration of early age, the effect of, just to analyze the maximum thickness we can have at the model, or also residual stresses on the model due to these thermal stresses, and to check and design by code calculation the reinforcement amounts, also the effects of ambient temperature and solid rotation, but in a model during the year, but not only that, also the effect of fire on the model, the effect of cooling, and some thermal isolations and fire protection. So we could analyze any type of thermal and nuclear power plant, a type of concrete that is holding a high temperature, also fire protection and the evaluation of temperature through it, and of course fire protection in different buildings, crack development. So we could cover any type of civil engineering and structural analysis type, and well, just any type of model.
Yeah, the important thing, as Roman said, always is that we CivilFEM does not take into account only the thermal analysis, but it couples both structural and thermal analysis, so we can always go beyond
yes,
to
and we can
obtain forces.
We can solve advanced nonlinear structural civil engineering models with CivilFEM in a very easy way and with an easy-to-use graphic interface, also using macros with Python. Well, if you are interested on some more details of CivilFEM, you can contact us here in these emails, and also in the website that we have here, the website CivilFEM.com. Here you can see also our local partners near to you, and also you can check next webinars we will have, and also you can check some trainings, some finite element trainings in the ICAEC center that we have, just for trainings and some more information.
Okay, and please, if you have some questions, you can place it now. We will answer them as soon as possible. And of course, take some time to complete a small survey that will open once the webinar is ended. Thank you very much. Goodbye.
Thank you for your attention.